Okay, can you hear me now? Fine. So I was explaining about depth-wise separable, sir, and I hope you got the point now that we are separating
Yes, sir.
the channel, we are separating the depth, and we are applying convolution over it. Okay, and that is how we are getting the depth-wise. Meanwhile, I requested everyone that you can run my code, and it's an easy way to create on the Kaggle. Okay, fine. And now let me share my entire screen to show you that particular thing. Okay, fine. Here it is. So here is my code. Here is my code, and what I go, how I follow the approach, you very well know that I create a data frames, columns, duplicate, null value, info, unique value counts, okay, showing the distribution of the images. So this is Alzheimer. This data set is having 8,000 plus 6,000, 9,000, 9, nearly 9,000. A good distribution of data set. Nearly 80,000, 38,000 something images are there with me. Okay, a good data set. And here then I have applied for five images from each category I have displayed, and then I did some part of resampling in order to balance the data set. That is what I did in this particular code. Okay, so I always keep my pattern of creating the code simple. Okay, straightforward. That is what I keep. Okay, got it. Fine. So, like you create a data frame which is having image path and the label. Okay, show the distribution of the images in form of count plot and the pie plot. The code is ready with you. Okay, and just show five images from each category. That is also you can do that. Okay, resample the images, like create a duplicate of minority class equal to the majority class. That is what you need to do. Okay, that's what you can do. Okay, and then later on, you can apply your algorithm. This is the algorithm or the technique, okay, which I applied. Here is the algorithm. And what I am doing in the algorithm, what is present? See, I have taken the data set, your MRI data set. I performed the basic transformation like resizing the image to 224, horizontal flip, 10-degree rotation, converting the image into tensor. Okay, high dimensional data. So this is some transformations I have applied. Okay, got it. Over training data. You can read your data, convert it into RGB format. This is very easy code. This is the code which I apply every time. It's a very easy code. Got it. So read your image, convert it into RGB format, apply the transformations over the image, divide it into training and the testing, and you can apply accordingly. So this part of the code is very easy code. You have to do on all the images which you take. So just copy and paste this kind of code on your images. Got it. And from here I made a hybrid model. And what I did, I took MobileNet V2, that is already pre-trained model over ImageNet dataset. And according to the transformer, I take an encoder layer. I applied an encoder layer. Okay. Where I am taking the dimension of the data to be 1080, 1280, number of heads I am taking 8. Okay, feed forward, that means the number of neurons I am taking 2048. So what exactly I am doing here? It's a very easy kind of perspective which I am applying. Okay, what I am doing? I am having MobileNet model. I am taking transformer encoder layer. Okay, transformer encoder layer. Now check this out. I am having an encoder layer. Number of layers I am taking two. Two such layers I am taking of encoder. Okay, got it. Fine. So this part is pre-trained model CNN based, and this part is transformer based. Both connection will make you a hybrid model. This will be a hybrid model. Okay, got it. Fine. The dimensions which I am taking in the encoder layer, okay, 8 head. 8 head. We are having 8 head, and over these heads only will perform that attention mechanism QKV. Over 8 heads only we perform this attention mechanism, QKV. You have seen that particular formula. So on every head, this QKV is performed, and later on the results are concatenated. I have taken 8 head. You can reduce the number of heads if you want to reduce the complexity of the architecture. That is what you can do. So whatever I am going to take from the mobile net, I will push it to the transformer. And from here only I am going to get a classifier. There are four classes are there that I can get. Okay. Number of classes. Meanwhile, I'm adding one linear layer also ahead of the transformer. Okay, ahead of the transformer, add a linear layer. And from here you can get a four classes results. So this is very easiest way I have done the task. Okay, so mobile net, two encoder layer, eight heads on each. That's the architecture. Very easy way. Okay, and you can see the results after training. You can see the results after training. 5 EPOs I have done with 5 iterations. I got 98 per. See, this is multi classification problem. Okay, how many images are there? 38,000 images. Multi classification problem. Getting 99% accuracy is a big deal, because getting high accuracy on multi classification is not an easy task. It's always been a tough task. Got it. But I achieved with MobileNet and proposed transformer encoder layer. Got it. And you can see, not hard and fast koi tough architecture I haven't made. It's not a tough architecture. I took, this is my hybrid model. I took MobileNet. I used transformer encoder layer. Okay. And two layers I have taken. You can increase four, you can increase three, four, whatever. Number of hits where attention mechanism is taken. Okay, you can increase if you want to increase the computational complexity of the model. You can reduce it also. Only this much is the architecture, the main game which we have played. Rest you have trained the model. Rest you have trained the model. That's it. You got the result. Okay, fine. Got it. 99% accuracy. Well, I have applied the same thing over one more data set, that is breast cancer. Let me talk about cancer also. Okay, breast cancer data set I have applied, and breast cancer data set is also having MRI, not ultrasound images like MRI only. Okay, grayscale images. Okay, got it. And if you see the code, if you see the code, okay, let me clear you from here. Just a second. All right, fine. Here is the first data set, and I will show you the code. Code will be like all together same, not a different. Only data set changes. This is breast ultrasound images. Breast ultrasound images. Okay, got it. I am having how many categories? I am having categories as benign, malignant, and the normal. Three classes are there. So this dataset is a benchmark dataset, which can be used for classification also, which can be used for segmentation also. Both it can be used. You can see that BUS UCLM separated, benign, malignant, and the normal. And once we are having BUS UCLM where images are present and their mask are present. So it's a dual purpose data set. Classification, segmentation, both can be applied. However, currently I have only worked with classification where I am taking separate classes. Benign, malignant, and the normal. This is what I am taking. It's a benchmark data set. Okay, got it. Now the code will be same followed. Creating a data frame. Okay, count plot, pie plot, five images from each category. Everything will be same. Doesn't matter Alzheimer, doesn't matter brain tumor, doesn't matter breast cancer. Same code is followed. Resampling in order to make the number of images equal. Same thing I did with Alzheimer also. Same thing I did with Alzheimer. Resample. Here also I did resample with the breast cancer. Creating duplicate of minority class and making it equal to the majority class. That is what I'm doing. Resample. Okay, got it. And then after that, after that, just check the architecture. The one which I have shown with the Alzheimer. Here it is. Here is with breast ultrasound. This is breast ultrasound. What I did, just only change the name. Instead of brain tumor, right now I'm writing breast ultrasound. That is what I'm writing. Rest everything is same. Hybrid model, same. MobileNet, transformer encoder, same I'm taking. Entire code is same. Just only dataset changed. And see the results. With 5 EPOs, 96%. See the confusion metrics, 96%. This is the result I got with breast cancer. Code also I've shared with you. But there is a twist. There is a twist. Now, what is the twist? ये तो this architecture which I am showing, it doesn't matter what kind of data set you are having, apply. Damn sure, damn sure I can give you right up, you will get high accuracy. Okay. Some components, some architectures I like very strong ones. But in the research paper they have written something more. Let me tell you what in the research paper authors are told, how or what kind of architecture they have made. Let me tell you what the authors did. Okay, authors are told that in their research paper they told that we made four stage hybrid architecture. That is what authors told. Four stage hybrid architecture. That's what the authors told. And stage number one is STEM. That means convolution. STEM. Initial layer. For low level feature extraction, that's the author told it's a STEM layer. That's what the authors told. Stage 1 and 2 is CNN based depthwise and pointwise convolution, which is present in the mobile net, which is present in the mobile net. So you can have some convolution first, then you can add mobile net. Stage 3 and 4 authors told transformer vit based. And then authors used a linear layer or a classification head. That is the final one. This is how authors propose their architecture. Four stage hybrid. Okay, if you want to see the research paper, here is a research paper. You can read it out everything from the research paper. This is your dynamic snake convolution. Okay, very good one. Whatever you get an idea, kindly use in your research also. And this is the architecture used by the authors. STEM is general convolution based. Stage number one, we are having inverted residual block. Stage number two, we are having depthwise separable convolution. Okay, one and two. Then three and four, we are having vision transformer. We are having vision trans. This is VIT block. This is VIT block. This is VIT block. And at the end, we are having convolution, norm, batch normalization, global average pulling, and out. This is the result. That's what the authors proposed. This is what the authors proposed as MobileNet plus plus. So in reverse bottleneck, inverted bottleneck, what we are taking here authors told convolution 3 cross 3 batch normalization deathwise separable convolution and pointwise separable convolution. This is what authors are saying in their architecture, IRLB, and this is VIT block, vision transformer block, according to the authors. And what I made, just took an inspiration from them, just took an inspiration from them. And I also did a code for retinal fundus classification, taking an inspiration from the authors. Okay, let me show you. So these are retina images, four categories, four ni, more than four. Again, it's a multi-classification problem. Okay, cataract, dry AMD, glaucoma, retinopathy. Many classes are there. Okay, what I did, see, these all are the classes. Multi classification again. I took the data set as I was doing, as I was showing to you previously. Same, in a same way, I took the data set. I took the data set. Okay, resize, and this is augmentation, simple kind of augmentation, as I did previously with the Alzheimer, as I did with the brain breast cancer. Same I am doing here with the retina. Same I am doing with the retina. Okay, now deathwise separable convolution, as per proposed by the authors. Convolution batch normalization, ReLU 6 convolution batch normalization. This is proposed by the authors. IRLB block. IRLB block. In IRLB block, inverse bottleneck. What we need to do? Narrow, wide, narrow. That is what we need to do. In order to do the narrow, okay, let's take the number of channels, input channel, input channel that will give from our side, output channel that also will give from our side. Okay, that that's the way we are making expand, then batch normalization, depthwise batch normalization, projection, batch, then again batch normalization, ReLU shortcut, that means skip connection. All these things are proposed from the research paper. Now, the one which I have shown to you and the one which I am showing right now is having a change. This is more self-made layer architecture rather than taking a pre-trained one. In the architecture Alzheimer which I have shown to you, I took pre-trained MobileNet, I took transformer encoder, and I did it. But here I am taking everything from scratch, adding the layers from scratch as mentioned in the research paper. Because if you see the research paper, this is what they have made from their own side. MobileNet plus plus means, okay, they haven't mentioned that we are taking MobileNet pre-trained. Can you see any of them pre-trained one here? Are they talking about any pre-trained MobileNet? No. MobileNet means they took the concept of MobileNet, inverted bottleneck. That is the concept they took. So first is the stem layer, convolution, batch normalization. That's it. Here is the stage number one. In the stage number one, they took inverted bottleneck, IRLB, with 32 channel, 16 channel, 27 channel. This is inverted bottleneck. Okay. And then again, then stage number two, depthwise separable convolution, inverted bottleneck, vision transformer block. See how the mind works, how to arrange the blocks, how to arrange the layers. Same thing I'm trying from my side here. Okay. And because there is a transformer, there should be an attention mechanism. So this I made separately. Attention mechanism, attention module. Okay, separate layer of attention. Here is a transformer where I incorporated attention. Okay, here I'm not taking any VIT, vision transformer, and here also I haven't took any VIT separately. What I did, I made a transformer layer with two encoder layer, and then here is a kind of some attention I applied, not multi-head and all, just a kind of an attention I applied. This is not exact architecture which is mentioned in the research paper. No, this is an inspired architecture. MobileNet with two encoder block or layer ahead of it. This is somehow what an inspired architecture. What I'm doing, see, mobile VIT block. Okay, this is MobileNet plus plus. Now listen, I am taking stem layer. They have mentioned na convolution normalization. Okay, check the research paper. Convolution normalization, stem layer. Okay, here it is. Here it is. Stem layer, convolution normalization. Stage number one. Stage number one. Uh, Inverted bottleneck. Two inverted bottleneck. Three inverted bottleneck. IRLB. Check. IRLB. 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 So I'm trying to copy the architecture which is mentioned in the research paper. Okay, how much? 16, 16, 32. That is what I'm trying just. Okay, 32, 32, 27. I'm just looking from my side whatever possible. Then DSC, depthwise separable convolution, VIT bottleneck. Then IRLB, check again. Depthwise separable, IRLB, VIT bottleneck. So I'm replicating, trying to replicate the exact architecture. Then sequential block, mobile VIT, stage number four. Then at the end we are having classification. Okay, check stage number four, stage number three, stage number four, VIT, and this is whatever possible from my end I tried. Okay, here is the architecture in front of you. So I am having stem, I am having some stages, two, three, four stages, whatever mentioned in the research paper. And with these stages, with these components, manually created, okay, not taking any pre-trained, not MobileNet, kuch bhi pre-trained, nothing, no pre-trained, just a manual architecture inspired from the research paper. I took, trained the model for 10 EPOS, and the accuracy which I achieved over retina is 65. 65. Sir, accuracy is very less. Everything is scratch. Okay. It takes time for training, and it was increasing also. 64 training, 65 testing. There is no overfitting. Not overfitting. Taking time to learn. I think I need to have 30 posts rather than 10. I should have used 30. Then it should be like 80, 90 nearly. You can change. You can change the number of e-posts from your side. Instead of 10, write 30. I applied the same concept over breast cancer also. See, this is breast cancer. Same approach I applied. I am having benign, malignant, and the normal three classes. I read the data set, breast ultrasound data set. I read all the things which I told you. I applied the same. Okay, this is depth-wise separable convolution. There are some comments also which you should follow. Dynamic snake convolution, DSC. Dynamic snake convolution. That is what proposed by the authors. Okay, so we should have an offset value. We should have a kernel size to create a dynamic snake convolution. Okay, I created that. IRLB same, which we are using in the Retina one. Okay, this is for inverted bottleneck, mobile net architecture. This is vision block, mobile VIT block. Okay, where I am having the transformer incorporated, proposed from the research paper. Transformer separate. This I will use here. This I can use here. Transformer I can use here. So I create a separate class transformer layer norm. Whatever be the input is, do the embedding apply multi-head attention, apply the normalization, that's it. So whatever happens in a transformer, everything is present here. This is MobileNet plus plus. Three classes are there. I trained the model. This is CNN, stage number one, STEM, stage number two, downsampling. Then depth-wise separable convolution. Now let's say dynamic snake convolution. VIT block, stage number four. This is the head for classification. Three classes are there. Train the model. Five EPOS. 44% test accuracy, and the problem here is normal images are not recognized in the test. Only 44% accuracy. That means still I require more training to perform the classification correct. I require more training. Classification is not perfect. Okay, I'm getting only 44% accuracy. Got it. Okay. However, when I applied MobileNet with encoder layer, MobileNet with encoder layer, I got 96% accuracy. But the one which I created from scratch, inspired from the architecture mentioned in the research paper, I am getting 44% accuracy. In which one class is over. गायब ही हो गया वो. One class is not showing. Zero. So creating a stem layer for feature extraction. Then inverted bottleneck, as mentioned in the MobileNet architecture, incorporating transformer blocks with the inverted bottleneck. Okay, and then final classifier header. This is the architecture of MobileNet plus plus. Got it. I have given you both the codes. This one also which is getting 96% over breast cancer, and this one also which is giving 44% over the breast cancer. But the point is, if you see the architecture as an inspiration from the research paper, d- dynamic snake convolution, we should have offset value. An offset value is present here in the research paper. This is offset value, delta pi. So you need to calculate delta pi. So this is the formula which you need to apply in the custom architecture. This is custom architecture, you need to apply this formula. This is dynamic snake convolution. Okay, rest is inverted bottleneck. Inverted bottleneck, narrow, wide, narrow. That's what you need to do in IRLB. Okay, then you are having transformer block. Okay, so for transformer, I am having this particular block of code which I can utilize here in the mobile VIT and overall MobileNet plus plus. So calling the stem layer initial, then inverted bottleneck, stage 1 and 2, then transformer blocks. Okay, and then classification head. These are the components. Okay, so score is less, but can be modified. Something which I like, what I tried from my end. At Alzheimer, it was like, sorry, at Retina, it was with 10 EPOS, it reached to 60 plus, 66 with 10 EPOS. With 30 EPOS, I guess it can be better. It can be better with 30 EPOS. Okay, but if you're taking pre-trained model and this one, only this one, sir, we don't want any like hard architecture. So this is looking good, sir. This is looking very fine. Take MobileNet and add to encoder. That's it, sir. 99% accuracy, sir. This one is good, sir. We'll follow this architecture. Okay, your choice. Your choice. But if you want to show dynamic snake, so snake is present here only, not there. Snake you will get here only. Got it? And here is the code for a dynamic snake convolution. And here is a formula for offset, which we are adding more in the from our side. If you refer to the research paper. So initial point, this is grid point, and this is the offset value. Whole make dynamic snake. Rest inverted bottleneck you can make from your side. Many changes you can do from your side. This is a very good research paper which you can apply on your data set. All right, that's what I need to tell, I guess, for today's class. Okay, I think that's for today's class. Okay.